All right, guys, I'm back on a sheet of paper because we're gonna need a little bit more room for this one. So in the last two videos, the first video, I introduced you guys to all the rules, all the basic rules for making deductions in TFL. Then in the last video, we covered conditional proofs, right? So these were the ones where you make an assumption and then try to show, try to prove a conditional statement. So if you're not okay with those, then go review some of that. Make sure you understand what a subproof is, how assumptions work, when you can pull from another subproof, when you can't. And today, in this video, we're going to look at proof by contradiction, okay? So these are going to be the two rules: negation introduction and negation elimination. Okay, these are both called proof by contradiction, okay? Proof by contradiction. Okay. So when you use negation introduction, it looks like this. Let's say you're trying to prove A and you have some premises, right? Maybe you've got some premises over here. What you can do is directly prove A. That was what we were doing in the last two videos. Or you can show that it's impossible for A to be false. Okay, let me say that again. You can show that it's impossible for A to be false. Okay, so how you do that is you say, hey, assume not A, right? So again, this is me starting an assumption right here, this vertical line. And you say, what if this thing I'm trying to prove over here is actually false? What happens then? Then you can do some steps. And if you get a sentence that looks like this, X and then negation of X, this right here, you recognize as a contradiction. Contradiction. Okay? Because if you have a sentence, if you prove a sentence is true and then you prove its negation is true, well, that shows that the sentence is both true and false. And we've set the entire system up in logic so that this is not possible. A sentence cannot be both true and false at once. Okay, that's called a contradiction. So if you can show that this assumption leads you to something impossible, like a contradiction, you can go conclude, so pop out of the subproof, you can conclude that A must be true. So again, this is more or less a proof that, I'm going to put quotes, it's impossible for A to be false. Therefore, A is true. Okay, so this is an argument that it's impossible for A to be false. And we can go the other way around too, and it works the exact same way. So we can also show, oh, by the way, this is called negation elimination right here. Because I started with a negation, I said that's impossible, so I eliminated it down here. This is negation elimination. By the exact same reasoning, if we're trying to prove the sentence not A, so I've switched things around now, right? We're imagining we're trying to prove the sentence not A. What I can do is say, hey, assume A. So again, it's the opposite of what I'm trying to prove, right? It's the opposite. So I do that, I get myself a contradiction. That allows you to say, hey, A must be false. This proves not A, okay? So this is a proof that it's impossible for A to be true. For A to be true, therefore not A, okay? So we do this in English all the time. We might say, well, like, if Eric's car is in the driveway, then he's home. Eric's car is not in the driveway. Therefore, it's impossible for him to be home, because if he was home, his car would be in the driveway, but it's not, right? So therefore, he's not home. That would be a contradiction. We'll look at an example of this, okay? So here's one of my favorite examples. I think it's one of the most simple ones you can do, is you can try to do a proof where you have this assumption, A implies B, or sorry, you have this premise, A implies B, and you have another premise, not B. Okay, then you can prove that A must be false. You can prove not A. So try to see, in this case, we're trying to prove not A, right? So our proof is gonna look like this one, right? Try this out real quick. Pause the video, try it out. Assume the opposite of what you're trying to prove. So go ahead and try to assume A. See where that gets you, okay? And see if you can use this proof to write your result not A. Okay, pause the video and try that out. All right, if you've done that, here's what you do. First thing you have to recognize is that we can't get to not A simply by arrow elimination, right? We can't do that because arrow elimination works like this, right? You can review the rule that we went over the other day. Arrow elimination says, all right, if A implies B and you got A, that means you can conclude B. But this is like backwards, right? We can't take this not B and use arrow elimination to get to not A because that's not how our rule is defined here. So we have to use a sneaky kind of proof by contradiction strategy to do this. So you can assume A, okay? And then over here in our textbook, they want us to put for reductio. Now, this thing is kind of an old Latin phrase meaning that you're trying to show that this thing is impossible, okay? So really, whenever you write this, I'm gonna put that you're seeking a contradiction. You're trying to show that there's something wrong with A being true. If you can prove that, that means A must be false. By this reason right here, right? It's impossible for A to be true, therefore I can conclude not A. So let's see what happens if A is true. Now look at sentences 1 and 3. That's just literally this, right? Arrow elimination. So I can use this to conclude B by arrow elimination 1 and 3, right? And now you can ask yourself, what do I know about the sentence B? Here, it's true, right? I've proven that B follows from this assumption, but I have as a premise not B. So what I can do is reiterate that sentence, not B. This is that silly reiteration rule I was telling you about in the first video, right? I can just restate the sentence not B there, and then look at this. B is proven to be both true and false inside this subproof. So this is not possible. This is a contradiction right here. This is what a contradiction is going to look like in your subproof. So because we assumed A and we got something impossible, we can conclude that it's impossible for A to be true. Therefore, A must be false by negation introduction. And you're going to cite that little subproof just like you do for conditional proofs. So you're going to cite lines 3 through 5, okay? So if you were to put this argument in English, you would say, hey, okay, A implies B, B is false, so prove that A must be false as well. And the way you could make this argument in English is you could say, well, okay, what if A were true? If A were true, then B would be true as well, right? By line 1. But then you end up in a situation where B is both true and false. That's impossible. So A must be false. A is not allowed to be true. So I'm going to put that here. A is not allowed to be true. Now, if you're learning this for the first time, this may seem like something really exotic and weird, okay? Right? It's like, why would we go through this kind of roundabout way of trying to prove not A by like assuming the opposite, trying to show a contradiction? But as it turns out, proof by contradiction is extremely useful, okay? And so I'm going to make an important note for you here. I'm going to put note, you can do any proof by contradiction. you can't do any proof, or I should say, you can't do all proofs directly. So if you want to 100% for sure be able to do a proof, the smartest thing to do, as long as you don't see how it's going to go right away, the smartest thing to do is start a proof by contradiction, because you know that's going to get you to your result. This can happen in easier cases as well. For example, in this simple proof, right? Okay, this would be a one-step proof where you would just use arrow elimination to prove B, right? This is a one-step proof, but let's say that you forget for a minute about arrow elimination. And so you're like, man, how do I prove B? What do I do? So you start a proof by contradiction where you say, hey, assume B is false. That would be this one right here, this strategy. Maybe you start a proof by contradiction. You say, all right, what if B is false? Then maybe you remember, oh yeah, that's right. I can use arrow elimination on these ones to get myself B. That would be arrow elimination on 1 and 2, right? Well then, wait a minute. There's your contradiction right there, right? There's your contradiction. And so once you get that, you can go ahead and say that, hey, this assumption must have been bad. I made this assumption and it led me into a contradiction right there. And so that assumption must have been bad. You can conclude that that assumption was wrong. In other words, that B is actually true. This would be negation elimination 3 through 4. Now, obviously, you don't need to do this for this proof, right? You can do it in just one step. But this is an example of how really you can do any proof you want with contradiction. And proof by contradiction is virtually guaranteed to give you the results you want, okay? But this proof over here, you cannot do this directly, at least using the rules that we have. If you're working with another textbook, you have like a contrapositive rule or something like that, then you can do this one directly. That's cool. But at least in our textbook, we can't use our rules on this guy. But proof by contradiction comes in and rescues us. It gives us a route for proving this sentence right here, without having to use our rules directly. And so you want to get really friendly with this idea of proof by contradiction, because really it's going to be used a lot in more complicated proofs, because sometimes your rules are going to kind of let you down. You're not going to be able to get something out of the simple rules that we covered. Okay, so let's look at more examples of this. Okay, now we're going to try a proof where we have no premises and we're just trying to prove C biconditional double negation C. Okay, so we have no premises now. So go ahead and take a minute to try to do this. Now remember, if you didn't watch last video, this is a biconditional statement and we know how to prove one of those, right? You assume what's over here, try to show what's over there, and then do the opposite, go vice versa, right? Assume what's over there, try to prove what's over here. So you know how to start this, but you're gonna have to use a sneaky proof by contradiction inside those little subproofs. So go ahead and try it. Don't get overwhelmed by the fact that there's no premises, because you know exactly the assumptions you need to make as long as you're comfortable with biconditional proofs. So go ahead and try that. Okay. So I'm going to run a standard biconditional proof on this guy. So I'm going to assume C, and I'm going to put want what's on the right side of the double arrow, right? Want not C. Negation, double negation C. Now again, maybe you're working out of another textbook and you have a double negation rule where you can kind of cleanly transition between C and double negation C with a double negation rule. But in our textbook, we have no such thing, okay? So first you want to recognize that this sentence is really the exact same as C. Exact same as C. Why? Well, if I tell you, hey, it's not raining outside, right? It's not the case that it's not raining outside. That just means it is raining outside, right? So double negations kind of cancel each other out. They kind of return you to the original sentence, because when you put a negation twice, it just changes the truth value from true to false back to true, okay? So that's the first thing to recognize, is that this is the same as the sentence C. It's no different. It's just got some kind of cumbersome negations hanging off it. So how do we show that not C follows from C? Well, we can do it like this. Suppose, again, so I'm starting another assumption here. Suppose C is false. And you'll see why we're doing this in a second. So I'll put for reductio. Assume that C is false. What's the problem with that? Well, line 1, right? Line 1 says I'm already assuming C is true, so clearly C is not allowed to be false. Not C is not allowed. And indeed, this is a contradiction right here, right? So because this is a contradiction right here, I can argue that this sentence must have been impossible, and the negation introduction rules allow me to slap an additional negation on top of this sentence right here. And that's exactly what we want, is a double negation C, right? So this is like, if you don't have a double negation rule on your hands, you can make an extra negation by saying, hey, assume not C. That's not allowed. Oh, okay. Here's your contradiction right here. That tells you that this assumption must have been bad, right? It must have been wrong. So therefore, you can negate that assumption out here. And this was what we wanted, right? We wanted to show that not C follows from C. Okay? I know this can be a little bit confusing because there's a lot of C's and a lot of negations. But again, just so that we're clear, you assume C because you want to show that this follows. Then you argue that not C is impossible because we're already assuming C. So you remind your reader in the proof, this is just housekeeping that we have to do. Yeah, this assumption makes a contradiction. So therefore you can negate that assumption, right? Because it makes a contradiction. You can negate that assumption. And this shows that, again, this is from the last video, this shows that C implies double negation C. Now we need to go the other way around, right? Because it's a biconditional proof. So now we're going to start a new assumption where we assume not C. And then in this case, we want C, okay? So how are we going to get ourselves to C? Well, maybe if you're starting to recognize the pattern here, you might think, oh, we're probably going to use negation elimination, right? Because we want to get rid of these negations right here. How do you do that? Again, at this point, pause the video, see if you can do it. Based on this, it looks very similar. See if you can get yourself to C. Okay, so here's what I do. I'm going to start a new assumption of not C for reductio. But then, look at this. I'm just going to restate line 5. Now look at this pair right here. I have a sentence, negation C, and then I have the negation of that sentence, right? Double negation C is just the negation of negation C, right? So this is a contradiction still. I have a sentence right here, and then I have its negation right here. This tells me that this assumption must be impossible, right? Because it's impossible, I can remove a negation from it and put C. This is going to be negation elimination, 6 through 7. And that is what I want, right? I wanted to show that C follows from this guy, not C. And I did that by using a very quick proof by contradiction right here, right? And so this proves the other way around, that not C implies C, right? That means we've got ourselves a nice biconditional of C and not C implying each other. So we get to use biconditional introduction where we cite both subproofs. So 1 through 4, that's the first subproof, 5 through 8. Okay, I know this can be, like I said, a little hard to look at because it's full of C's and negations. And maybe if you're a student watching this who's been given a double negation rule, this will look a little bit appalling because, if you have a rule that lets you transition from here to here, things are from C to double negation C, things are nice and easy. But like I said, we have no such rule. So every time we want to handle a double negation, we have to run a quick proof by contradiction like this. Okay, and again, make sure you keep track. I'm assuming that maybe you're doing this problem on your own. Make sure you keep track of which assumptions are running where. These vertical lines tell you that, right? Which assumptions are running where. You want to make sure you keep track of this stuff. Both of these are done under the assumption of not C. That's why I have this vertical line here. Okay, but all of this is done under the assumption of C. Okay, that's why this whole vertical line on the inside runs from 1 to 4. All right. Okay, so the next one we want to do is going to be, let me see. We're going to do this guy. So we're going to get A or B. And then we're going to get A double arrow B, and then we're going to try to prove A and B. Okay, so go ahead and try this out. All right, so here's what you might have done. You might have said, okay, well, I can't really get anywhere directly with the rules, so you might have said, let me negate this whole sentence right here. And certainly that is one way to do it, is you can just negate this whole sentence out here and try to work with that, show that that leads to a contradiction. But there is an easier way to handle this that I think kind of makes more sense. If we're proving the sentence A and B, that means we should be able to prove each of these sentences separately, right? If I'm trying to prove that, it's raining outside and my socks are wet, then I should be able to prove separately that it's raining outside and separately that my socks are wet. So I'm going to run a proof of A and B separately, okay? And here's how I'm going to do that. I'm going to assume not A. And this is with the idea of trying to show that not A is impossible. So I'm going to put 4 reductio. What can I do now? Well, I can use OR elimination on lines 1 and 3, right? This tells me one of them's got to be true. Now I'm saying it's not A. All right, well, B must be true then by OR elimination on 1 and 3. Okay, what else is true if B is true? Oh, look, A and B imply each other. That's what line 2 says. So this leads me straight back to A by biconditional elimination on 2 and 4. And that is a problem, right? Because we're already working under the assumption that of not A, pretty much, right? We're already working under this assumption. So I got to restate line 3 just because our textbook requires us to put the contradicting sentences right next to each other. So I'm going to say this is a contradiction. Now they're right next to each other, and whoever's grading your problem set or your exam can see, oh yeah, there's the contradiction right there. It's just a way of keeping things tidy and clear. So this contradiction right here tells me that this assumption was bad, right? Not A is not allowed by these premises because it leads us into this contradiction. So I can go ahead and conclude A by negation elimination 3 through 6. That's that subproof, right? 3 through 6. Great. So I've got I've got one of these guys done with. See if you can prove, this is why I like problems like this, is we can do a proof of B in a very, very similar way. So if you're watching this trying to understand what's going on, try to prove B now in the same way that I proved A and see how that goes. Okay, so if you've tried that, here's what I'm going to do to prove B. I'm going to assume not B for reductio. I'm going to say, let's argue that it's impossible for B to be false. That would prove that B was true, right? And then if I have not B, I can use disjunction elimination again, right? It's A or B. Here I'm saying it's not B, so it must be A. Disjunction elimination on 1 and 8, right? Again, if I'm going through these rules a little quickly, make sure you have that note sheet next to you of all the rules so you can kind of keep track of what's going on here. But then look, line 2 says that A implies B. So I can take this A and get B from it through biconditional elimination, right? 2 and 9. And there's your problem right there, is that we've already assumed B is false. So I'm going to restate that. Hey, wait a minute, B is false. That's the whole idea of our subproof, right? And I just proved that B is true from that assumption. So that's not allowed. So this is a contradiction, which tells me that this assumption right here must have been bad. It must have been bogus, right? So I can take that negation off of it and prove B. This will be negation elimination 8 through 11. So that's nice. I mean, I've proven A and B separately. So all I got to do to get myself this sentence is just slap them together with an and symbol. A and B. And that's and introduction from lines 7 and 12. 7 and 12. And that is my result. So that concludes the proof right there. So yeah, like I said, you could start by assuming not A and B, but just because of the rules that we have, this sentence is difficult to analyze. If you have like De Morgan's laws or something on hand, this becomes relatively okay, but this should get you your result as well. It's just a little more tedious. Proofs with and statements like this, I like to kind of usually approach them as proving both conjuncts separately. Because in an and statement, both conjuncts have to be true, right? So you can prove them separately and get the job done that way. All right. What's up next? Okay, we're going to have, I'm going to draw a line right here. This one is next. We're going to have premise 1 is going to be S implies R or T. Premise 2 is going to be R implies not S. And then we're going to try to prove that S implies T. Okay, so remember, conditional statement right here, right? So automatically be thinking, I'm going to run a conditional proof on this thing, and then I'm going to see what happens, all right? So go ahead and give that a shot. See how it goes. Okay, so I know how to do a conditional proof, right? Assume whatever's on the left. So that's just like automatic start right there. Assume S, try to show that T follows. And then I'm, expecting that we're gonna have to do some weird proof by contradiction type stuff in here. Okay. So S implies R or T. Right? That's what line 1 tells me. And now I'm supposing S is true. So that would mean that R or T must be true by arrow elimination on 1 and 3, right? S implies R or T, and here S is true. So that makes R or T true as well by this rule. Okay. Where am I at now? Well, I'm trying to show that T follows from S, right? And here I have the statement that one of R or T is true. So I'm kind of thinking like, all right, probably it's going to be T, but what would happen if R was true? Because if R is not true, that would mean T has to be true, right? If we can find out that this guy is false, that means that T has to be true, and that's what we want to show, right? So let's find out if R has to be false. What happens if R is true? So here I'm starting another subproof for reductio. What happens if R is true? What would that mean? Well, look at line 2 here. If R was true, that would mean not S was true. So I can use this to get not S from lines 2 and 5, right? And this is arrow elimination, 2 and 5. But wait a minute, this whole subproof is under the assumption that S is true. So at least in this assumption, it looks like R is not allowed to be true, right? Because if R is true, it makes not S by line 2, right? And then that would lead me to this contradiction right here. Because that would mean S was false, but S is true. So S can't be true and false at the same time, right? So this means that when we're assuming S at least, R cannot be true, right? Negation, introduction now, 5 through 7. So again, this contradiction right here shows you that this assumption is bad. R is kind of not allowed to be true in this context, right? Because if it is, it leads you straight into this contradiction. So that means that not R. Okay, well now look at sentence 4. Not R, one of R or T has to be true, right? And if it's not R, okay, well, T then must be true by disjunction elimination. And this would be 4 and 8 now, right? And look, that's exactly what we wanted, right? Great, we got to the end of our conditional proof. We showed that T had to follow when you assume S, and that involved this kind of fun little proof by contradiction in here for R. So I showed that T followed. That means I can write my result, S implies T, by good old-fashioned arrow introduction, and then cite the whole subproof 3 through 9. Okay? So there's going to be a lot of this going on in future problems. It's like you're going to run a conditional proof, and then somewhere in that journey on the way to T, you're going to have to throw in like a proof by contradiction inside whatever you're doing. So again, it's proof by contradiction is nice because you can prove pretty much anything with it. But yeah, sometimes you're going to have these kind of nested subproofs. That happens pretty often with proof by contradiction, okay? All right. So I got one more for you guys. If you're a student at UIC, this will be on problem set, let me see, problem set 6. This was one of the problems, is we want to prove from no premises this statement, P implies Q, or not Q. Let me draw a line right here, okay? P implies Q or not Q, and we have literally no information. We have no premises. We're just asked to show that this is true. So let's think about strategy a little bit here. We could try to prove the sentence P arrow Q, and then use or introduction to get our result, right? But how are we supposed to prove that P implies Q when I don't have any information about the relationship between P and Q? I don't have any premises where I can assume P and show that Q follows, because right now they're just two sentences that don't have any relationship to one another, right? There's no premises. So this is going to kind of be a non-starter right here. I can't prove this thing with or introduction. And similarly, I can't prove not Q and then or introduce this guy. Because how am I supposed to prove negation Q is false in the first place? I don't have any information about it. There's no given information. So this is going to be a non-starter. So what I have to do is realize that this sentence by itself has to be absolutely true. This whole sentence, P arrow Q or not Q, it must be true. This is called a theorem. It's got to be true from no premises. And that means if it's not true, there's going to be some kind of big problem, right? This is true just based on no premises. So if I go ahead and assume that it's false, I should expect to run into a big problem. I'm going to put for reductio here. So notice that all I did was take the sentence I'm trying to prove and slap a negation out front, right? This is the negation of what I'm trying to prove, and I expect there to be some kind of contradiction hidden in here. So go ahead and see if you can find that. This one's a little bit tricky and a little bit long-winded, so go ahead and see if you can find it. Okay, so if you're a student watching this, again, you have something like De Morgan's laws in your textbook, you can start dealing with this thing pretty quickly. But in our system, we don't have these rules. So what we have to do is kind of interpret what this sentence is telling us. If you look at what this is an or statement, right? I've got P arrow Q or negation Q. So the thing inside the parentheses is an or statement, and then it's negated. So let's ask ourselves, what do we know about a negated or statement, right? This is just a generic looking negated or statement out here. Well, here's what our truth table for it would look like. Right, there's 4 cases: true, 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 false, false, true, false, false. And the or statement is true in 3 cases, as long as at least one of the disjuncts is true, right? It's only false in this case. But then throw a negation out front and it reverses all the truth values, right? So then it becomes false, 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 true. So these are the truth values of our negated or statement. Now look at what this says. It's only true in the case that both of its constituent sentences are false, right? So a negated or sentence actually gives us a lot of information. If this sentence is true, it tells us that X must be false and Y must be false. So there's actually a lot of information hidden in here, right? And that's exactly what we're gonna use on this thing right here. So because this is a negated or statement, I know that this sentence must be false, or excuse me, I know that negation P arrow Q must be true, right? Because one of this sentence is joined by the or symbol must be false, and I know that this guy must be false too. So I know that negation Q must be false, but as we just learned, this sentence is the same as Q, right? So I just learned something important, is that this sentence right here is telling me that Q must be true. So we can use that to guide our strategy here. I know now that Q must be true. So here's what I'm going to do. I'm going to do a proof by contradiction of that. So I'm going to assume not Q and show that that leads to a big problem. So again, pause for a minute if you want to, see if you can figure out the problem with not Q. But here's what it is. If I assume not Q, then I can or introduce this statement, right? Or introduction from 2. Because or introduction allows me to put any other sentence I want with the sentence not Q, as long as it's with an or symbol, right? So if not Q is true, then this sentence must be true as well. But then that contradicts line 1, right? Line 1 tells me that that whole sentence is already assumed to be false. So look at what we got here. This can be a little hard to recognize sometimes. This is a sentence, right? And this is the negation of that sentence. So this is a contradiction. This pair right here is a contradiction. That tells me that this assumption must have been bad, right? This assumption must have been bad. So I can take the negation off and conclude Q. Because not Q is not possible right now, right? Not Q would lead to this contradiction right here. So therefore Q is true. And all this business was me looking at this sentence and using that to guide what my next assumption was going to be. Okay. Now what are we going to do? We got the sentence Q, big whoop. What are we going to do now? So let's see, what can we prove from Q? Well, if we think about what we're doing in here, we're back in subproof number 1 right now, right? This thing did its job. We're back in subproof number 1. And we're fishing for a contradiction, right? That's what this whole thing here is for, right? We're fishing with some kind of problem with line 1. So here's the thing. If I got Q, I can do a really easy proof that P implies Q. All I have to do is assume P, want Q, restate Q, and I got myself, oh no, okay. I'm gonna have to X that out, sorry. Apologies if this is confusing, but this is a proof that P implies Q. 6 and 7, okay? So this is, sorry about this messiness here. This is going to be outside this subproof, 6 to 7. So if you have a sentence, this is kind of a trick you can do in logic, is if you have a sentence like Q, pick whatever you want, like P, pick whatever sentence you want, and you can easily show that that sentence implies the sentence you already have, right? All you need to do is start a conditional proof, restate that sentence, great, that's a proof that P implies Q. And this is important because I can use or introduction on this guy again, right? I can say P arrow Q or not Q, or introduction on line 8, right? I've proven now that P arrow Q is true, so that means that this statement has to be true because one of its disjuncts, one of its disjuncts is true. But of course, this is not possible in light of line 1, right? Line 1 is the negation of this sentence. So I repeat line 1. Line 1 is the negation of this sentence. This is the exact contradiction that happened all the way up here in our subproof, right? It's just happened again. These two things contradict each other, right? You got sentence here and then it's negation right here. So you recognize this as impossible. And we're back in our first subproof. So there it is. We showed that this assumption right here, when you start exploring the logical consequences of it, you get something very contradictory looking. And so that tells you that that original assumption up here must have been false, right? It's impossible for this sentence to be false. Because if it is, we get this big contradiction down here. So that allows me to take the negation off this sentence in line 1 and write my result. And I took the negation off the sentence in line 1, right? So that's negation elimination, 1 through 10. And that concludes the proof right there. So again, if you're maybe another student not from the University of Illinois, Chicago, and you're watching this video, you might be a little bit appalled if you have De Morgan's laws or something like that lets you kind of make nice transitions here. But hopefully, if you're in this position, then maybe this gives you practice using proof by contradiction because it is a great tool. Yeah. Okay. Next video, I think this was the last one we wanted to do today. Yeah. So next video, we're going to do some more difficult proofs where we're going to try to use everything we've learned in the last 3 videos. And hopefully that's going to give us some practice with with kind of using all of our rules at once, okay? So this is pretty much all the material that you need to learn, at least if you're at UIC taking your final exam. This is pretty much all you need to learn. But I'm going to put out another video where we kind of do some more difficult problems so that you guys hopefully feel confident with this material and can do some more difficult stuff. Okay, thanks for watching. See you guys next time.